All right, so here's another kind of problem. So we're given the initial concentration of carbon-14 a slide or two back, and we want to know after 120 years what's it going to be. So we need to start off with our equation, and it's probably a good idea to memorize these equations. On the ACS final, they kind of expect you to know them, but I would say that just through using them a lot, you'll probably learn them. And we want to know the concentration at time t. We're given the initial concentration back a page or two. We're given K, and we're given the time in years. So we probably need to start off by converting the time into more sensible units. Our rate constant has got units of per second, so that means that probably we need to get our time in seconds. And so this is a very nice kind of factor label problem. We got 120 years. We know that in 1 year there's about 365 and a quarter days, and so on, right? 1 day is 24 hours. 1 hour is 3,600 seconds. And so if you calculate this, you'll get the time in seconds. And if you do that, you get some enormous number, right? 3.787 times 10 to the 9 seconds. And there's probably a guard digit right there. All right, so let's have a look back up. So we've got everything on the right. We got K, we got T. We know what minus is. And we've got the initial concentration. And we need to find this. And so we need to play. And there's lots of ways you can do this kind of problem. One thing you can do is you can use the property of logarithms we saw earlier. That is whenever you got the log of one thing over the other, that's the log of one thing minus the log of the second thing. And so if we've got log of concentration at time t over the original concentration, we can break that down and make that the log of a sub t minus the log of a sub 0. Oops, wrote the wrong thing there. And we're saying that that's equal to minus kt. What do we know? We know this, we know this, we know this. We need to solve for this. So we can go ahead and we can manipulate the equation. We can say the log of the thing we don't know is equal to the log of the original concentration minus kt. So that's the log of the original concentration of carbon-14, which is 5.83 times 10 to the minus 11. Okay. And we subtract away from that K, 3.83 times 10 to the minus 12 per second. Okay, and we're multiplying that by the time, and the time in years was enormous, right? And so this was 3.787 times 10 to the power of 9 seconds. And so here our units are canceling. We're actually being a little bit naughty taking the natural logarithm of a number with units. It turns out there's another way to do it that avoids it, and it will come out right, but it will make the math department cringe. Now, if you go ahead and you calculate the right-hand side, I get that to be a very small number, minus 23.5799. And again, probably carrying way too many significant figures here, but I'm really worried. If we take logs and anti-logs, these things can blow up. So you probably need to use the unrounded number on your calculator. We want to get rid of the log, so we anti-log, and anti-log, poof. That means we take e to the power, so e to the power of the right-hand side, e to the negative 23.5799. And if you calculate that, it's a very small concentration. Let's do that on the line below. And it is 5.75 times 10 to the minus 11. And that's a concentration, so that's moles per liter. Another way we could have done this problem actually is gone back and stolen our old equation from before. A sub t is a sub 0 times by e to the minus kt. That way, actually, the units would have come out nice. We wouldn't have had to take logarithms and anti-logarithms of things with units. It probably would have been more honest. Wow, okay, so the concentration at time equals 0 started out 5.83 times 10 to the minus 11. And after, 120 years, it only went down by the tiniest amount. So 5.75 times 10 to the minus 11 years. So that's an incredibly tiny change. In fact, this is really not a good example at all. It turns out that carbon-14 dating is really not that good over a 100-year period. And so really, 100 is kind of pushing it. Normally, 100 is the very low end. Normally, 1,000 is what we would start with. And it turns out that we can date things that have been dead or were living anywhere from 1,000 to 50,000 years ago. Why 1,000? Well, actually, you can see after 100 years, it's really only gone down by some fraction of a percent. Hard to measure. After 1,000 years, it would go down significantly. Why 50,000 years as an upper limit? Well, after about 50,000 years, there's hardly any carbon-14 left. It's really difficult to measure that concentration. The geologists will know that there's lots of other radioactive atoms that have a much longer decay period. For instance, potassium, uranium, lead. These guys, you can date things on the order of millions or billions of years.